Good morning, all of you TyBsc physics student. We have to see our subject is solid state physics, and we want to continue the third chapter, which is pre-electron and band theory of metals. And today we want to start the points of Sommerfield's pre-electron model. Summary of the last lecture, we have to see here the classical free electron model, which is used to classical statistics, which is considered as Maxwell-Boltzmann statistics, and we have to see idea what is understanding the concept about the classical free electron theory. In this lecture we want to start the quantum theory, or we have to consider here the new point, which is the Sommerfeld free electrons model, which is based upon the quantum free electron theory. So in last lecture we have to see about here the valence electron of constituent atom, which is move freely throughout the volume of the metal, which is considered as the gas molecules which is moves in a vessel. But this free electron theory, which obey the law of quantum mechanics rather than the classical mechanical model, which is considered as Boltzmann distribution, Maxwell-Boltzmann distribution. And this quantum theory, the Maxwell distribution or Boltzmann-Maxwell distribution, which is replaced by Fermi-Dirac distribution. So that first point on this assumption of this model, which is considered as this model, which is replaced by the classical statistics, which is the Maxwell-Boltzmann by Fermi-Dirac statistics, and which here the metal which is replaced by a box containing non-interacting free electrons. Okay, so this first assumptions which is considered here the quantum free electron theory, so that Maxwell-Boltzmann distribution, which is replaced by quantum theory, in which using help of obeys the law of Fermi-Dirac statistics, and this metal which is replaced by, which is considered as the box containing the non-interacting free electrons. Next assumptions and next point, which is considered as these free electrons which is in the atom or box containing, it obeys the Pauli exclusion principle. This is the main point. And next point, which is considered as this free electron in a solid moves as if it is a system of waves. So in quantum mechanics we have considered the as a particle which is replaced by, or consider the study of in terms of the waves, and the number of permissible state for an electron to occupy in the potential box, which is calculated by the Schrödinger equation. So we have to consider here, so this model which is proposed by the Sommerfeld in 1928, and that he assumed that the valence electrons which is travel in the constant potential inside the metal, and these electrons are prevented from leaving the solid by very high barriers of the boundaries of the crystal. So that is in short, which is considered as the electrons are trapped in the constant potential well, which is shown in figure. We have to see if next point. So what type of this potential barrier, and what is the potential energy, and what is kinetic energy is there, and what is the formula used for the Schrödinger equation, which is used as like this, so which is seen further few minutes. So that number of permissible state for an electron to occupy in the potential box are calculated by the Schrödinger wave equation, and this distribution of free electrons in the various permissible state, which is answered by applying the Fermi-Dirac distribution. So in next point we have to see here the energy levels and density of state in the one dimension. So once again revise this. So that classical free electron theory that replaced by the quantum free electron theory, and in this theory we have to replace this Maxwell-Boltzmann distribution by Fermi-Dirac distribution, and metal which is replaced by the box containing the free non-interacting electrons, and these free electrons which obeys the Pauli exclusion principle. And this is the point which is the electrons moves in the solid, which is the system of waves, and this distribution which is help to understand the obeys the law of Fermi-Dirac distribution. Now next point we want to start here, the energy levels and density of states in one dimension. So energy levels and density of states. Energy levels and density of states in one dimension. So energy level and density of state in one dimension. So that consider free electron which is considered of mass m, which is confined in a box, and that box which is considered as the length L, and assume that potential energy everywhere within the crystal which is considered as 0, and that two ends of the crystal the electron prevented leaving the crystal by a very high potential energy barrier. So we have considered here that potential box or energy barrier which is considered as the figure. So that is one dimensional potential box which is considered, for example, so this is the energy barrier of one dimensional potential box which is considered as the potential energy that V is equal to 0 in the box, and this box that barrier length which is considered as the infinite. Okay, and if we consider the barrier length which is considered as this is x is equal to 0, and this length of barrier which is considered as that x is equal to L, so total length which is considered as L, and this diagram which is considered as one dimensional potential box. One dimensional potential box. So we have to already see that free electrons which is considered as 1D potential box, that potential energy that V is equal to 0, and that boundary barrier which is for the infinite state for length which is considered as the first point, that boundary condition which is considered as x is equal to 0, and second boundary condition which is x is equal to L. So total length of this barrier which is considered as L. So we have to apply the Schrödinger time independent equation in one dimension. So is given by, so which is given by h cross square del square psi of x plus v of psi is equal to E. So the Schrödinger time independent equation Schrödinger time independent equation, and this Schrödinger time independent equation which is considered as minus h cross square divided by twice m into del square psi, that is considered as d square psi by dx square d square psi by dx square plus v of psi is equal to E of psi. So this is equation number first. That is the Schrödinger time independent equation. So that is minus h cross square divided by twice m d square psi by dx square plus v of psi is equal to A of psi. And consider for this region the potential which is considered as the V is equal to 0. So for this region potential is 0, that is V is equal to 0. If we placing this value is here, so this equation will obtain here. So minus h cross square divided by twice m into d square psi by dx square is equal to E of psi. And if we rearranging this equation, so that remaining part which is considered as d square psi by dx square is equal to this minus this side, so minus h cross square divided by twice m, this is going to this side, RHS side, so which is here, so twice m divided by h cross square of E of psi. Okay, and if we this equation which is coming for this LHS side, so this equation will become d square psi divided by dx square plus twice m E divided by h cross square of psi is equal to 0, and psi which is nothing at or psi which is considered as the wave function. So this is considered as the d square psi by dx square plus twice m E divided by h cross square of psi is equal to 0. So if we consider this twice m E upon h cross square is k vector, so that k is equal to or k square is equal to twice m E divided by h cross square, twice m E divided by h cross square. And if we taking the square root of this equation which is considered as this equation is here, so d square psi by dx square plus k square psi is equal to 0, so this is considered as the equation number third. And we have to know that taking the square root of this value, so that k is equal to under root of twice m E divided by h bar square, So we have to take this general equation of this equation which is given as so general solution of equation 3, which is considered as psi of x is equal to a sin of kx plus b cos of kx. So this is the general solution of this equation. So a psi of x is equal to a sin of kx plus b cos of kx. A and b which is considered as the arbitrary constant. B is arbitrary constant. Okay, or in figure we have to see here. So that boundary condition which is applying here, so that here potential is 0. So this barrier side which is going to further infinity, and the length which is considered as x is equal to 0 to x is equal to L. So applying this boundary condition, so that electron wave function has to satisfy the following boundary condition, and we have to see here. So that applying boundary condition, so first condition which is considered as at psi is equal to 0, when psi is equal to 0, when at x is equal to 0, and second boundary condition which is considered as psi is equal to 0 when at x is equal to L. So by applying the first boundary condition, so what equation which is coming here we have to see here. So general solution of this equation which is considered as a sine of kx plus b cos of kx. So we have to see here. So this is first boundary condition and this is second boundary condition, and applying first boundary condition. Okay, so that equation which is considered as psi of x is equal to a sine of kx plus b cos of kx, and the boundary condition which is considered as at x is equal to 0. If we see here, so that psi of 0 which is given as a sine of k0 plus b cos of k0. Okay, if we see here, so at first boundary condition, that condition psi is equal to 0 when that x is equal to 0, so that is given as 0 is equal to this a sine of k of 0, and sine 0 is 0, so that is 0, and cos 0 is 1, so that is considered as b. So that first applying boundary condition, so vector which is given as b is equal to 0, this is by the first boundary condition. By applying second boundary condition, second boundary condition, so that is at x is equal to L, at x is equal to L, so which is considered as this b part which is given the solution, so that b is equal to 0. So next boundary condition which is for this relation, so that relation which is considered as star. So for applying boundary condition for this, so that given that psi of x is equal to a sine of kx. Okay, and if we apply this boundary condition, so that relation which is given according to boundary condition psi is equal to 0 at x is equal to L, so this is 0 is equal to a sine of kl, and this is given as the equation number 7. Okay, and we have to see here the point. So next, by according to apply the boundary condition, so that relation this kl which is nothing but consider as kl is equal to n pi, so that k which is considered as k which is considered as n pi divided by L. N is the quantum number, so that relation will give here, so that n value which is considered as n is equal to 1, 2, 3 up to so on, that is integer number, and n is equal to 0, so that represent this n is represent the order of the state, which is considered as order of state, and n is equal to 0 is not allowed condition. So this is the main condition for according to the boundary condition of second, that n is equal k is equal to n pi by L, and solution that 0 is equal to a sine of kl, and therefore this solution of the Schrodinger equation in the region of 0 is less than x less than L. So the solution of the Schrodinger equation in region which is given by here, the solution of Schrodinger equation Schrodinger equation in the region which is this region which is given by 0 is less than x less than L, because we have to know that that figure which is considered as that potential V is equal to 0 infinity to infinity, and which is considered x is equal to 0 to x is equal to L. So that region which is considered as 0 is less than x less than L, so that is total length which is considered as L, and the relation which obtained here, so that solution which is considered as a sine of kl, and that k value which is nothing but the n pi L, and which is considered as the x. So putting this k value in equation 7, so that relation or the solution which is given here, so that psi of x is equal to a sine of k value which is given by n pi divided by L into x, so that is considered as in one dimension. And if we equating equation number 4 and 8, so that equation number 4, that value which is given by or k value which is given here, so that first condition, so that k which is given as twice m e divided by h bar square, so that is the k square value, and according to here k value which is given by n pi by L, so that given value k square which is here n square pi square by L square. So for example, this is equation number 8 and this is equation number 9. Okay, so for equating this equation number 8 and 9, we have to given here value of the E. So for nth level, so equating the equation number 8 and 9, equation 8 and 9, so we get, so k square value which is considered as twice m e n divided by h cross square is equal to n square pi square divided by L square. So this equation will get here, so that En is equal to n square pi square h cross square divided by twice ml square. So this is the nth level energy. So this is indicate that the energy is a function of the quantum number n, and indicate that the energy levels of wave function of energy of mass m, which is confined to the line of length L, and these energy levels are labeled, which is according to the quantum number n, gives the number of half wavelength of the wave function. So that this equation indicate that the energy is a function of quantum number n. So this is equation number 10. This is the energy of nth level. So that is considered as the energy is a function of quantum number n. Energy is a function of quantum number L. Okay, so now if we analyze this figure, so that first three energy levels how it occupy, which is see in the next lecture. So thanking of you.